Nikhitha. I am from GPT Masabtank. So before going to my topic, I want to introduce my parents. So my father is a farmer and my mother is also a farmer. My father name is Tirupati and my mother name is Lata. So coming to my topic is Successive Approximation Register ADC method, analog to digital converter method. So what is mean by ADC here? ADC means here it converts the analog information into digital information. So here input is in sinusoidal waveform, means fluctuated input. So output is here digital signal, means zeros and ones. So why we need ADC, analog to digital converter? Because when you will transmit the information from transmitter to receiver, there will be effect of noise. So the information what we see around us, like electrical currents, tides, or my speech, or even our heartbeat is also in analog information. So in order to transmit this information, there will be effect of noise and the output will get distorted. So in order to get undistorted output, we will convert the analog information into digital information. So we will get undistorted in output at the receiver. So and another one important is, when you want to process the computer or you want to store the information in memory, then you will store it in memory, right? Then but the memory can understand in ones and zeros. If you give information in analog format, then how can memory can understand it? So the analog information must be converted into digital information in order to store the information for future generation. So that's why we are converting the analog information into digital information. So one of the method of analog to digital converter is Successive Approximation Register ADC method. So what is mean by successive approximation? Let us discuss with an example. So if you want to measure something material, I am considering here stone. I am considering it is as an analog input. And it is a digital output. It is a desired one. And consider it is as a operand. So whenever you want to measure the stone, then what you will do? You will add the weights to the operand, right? So we will add here. We will add. For example, 1 kilo, 1 kilograms or 100 grams in order to balance the desired ones. So you will add, means you will reinforcing or you will decreasing the weights in order to balance the desired ones. So if I am adding 1 kilogram, 1 kg, then if it is greater than desired one, then you will remove it and you will add lesser weight. And suppose I am adding 500 grams. If 500 gram is lesser than the desired one, then you will remove it and you will add greater weight. So in order to balance the desired one and the operand weight, you will reinforcing or you will adding or removing the weights. So in order to balance. So here also the digital outputs are, here at the digital output we are adding the bits or we are removing the bits in order to balance the analog input voltage. And let us discuss about the block diagram of the successive approximation. So here it is also called as trial and error method. Because we are trialing the weights, right? And we are getting analog input with corresponding digital output. So that's why it is also called as trial and error method. Coming to block diagram, here the main blocks are comparator, control circuit and successive approximation register and digital to analog converter. So what is mean by comparator? So the op-amp without feedback, the application is called as a comparator. So there is no feedback, right? So that's why it is called as a comparator. So comparator has two inputs, one is non-inverting input and one is inverting input. So we are giving our information, that is analog input voltage we are giving to the non-inverting terminal and the output of your DAC we are giving to the inverting terminal. So whenever let us consider analog input voltage as a Vin and output of your DAC is V reference. So whenever Vin is greater than V reference, then the comparator output is logic 1. So whenever Vin is less than V reference, then the comparator output is logic 0. And next, control circuit. So control circuit is used to reset the present set bit, and whenever Vin is less than V reference, it is used to reset the present set bit. So whenever Vin is less than V reference, it is used to reset the present set bit. Present set bit. And whenever Vin is greater than V reference, it will retains the present set bit. So whenever Vin is greater than V reference, it will retains the present set bit, means it will put as is. And next block is SAR, Successive Approximation Register. It contains 3 inputs, one SOC, EOC and clock. So, SOC means start of conversion. If you want to convert the analog information into digital information, then you will give start of conversion. And if you want to end the conversion, then you will give end of conversion. And a successive approximation register contains a ring counter, which is successively set one by one bit from MSB to LSB. Basically, it starts from MSB and next it transfers the MSB bit to the LSB. And here we are taking 4 bits. So this is also called as a 4-bit successive approximation register, ADC method. And here the ring counter contains 4 bits. We are taking 4 bits, right? So that's why it is called as 4-bit. And next, DAC. So DAC is a digital to analog converter. So in order to compare the analog input voltage, we are converting the digital input to analog input. And let us consider this output resolution as a 1 volt. So whenever the digital input changes 1 LSB bit, then the corresponding analog voltage changes by 1 volt. Here one note point is, so here the corresponding binary number is 6, means 6 volt. It does not consider like that. So we are with respect to resolution, we are considering output of an analog voltage. So if you take 2 volts, resolution as a 2 volts, then for every LSB bit change in LSB bit, then the corresponding output at the analog will changes by 2 volts. And next, let us go for the working condition. So whenever we are giving start of conversion, means whenever we are giving start of conversion, it will reset the internal register, means it will reset, means here the output of SAR will be 0 0 0, means here we are taking 4 bits, right? So that's why 4 bits are zeros. Whenever we are giving start of conversion, it will be 0 0. So the corresponding voltage of 0 0 0 is 0 volts. Here the first one is 0 volts. So next, I am assuming that the analog input voltage is 10 volts. It is a unknown voltage, but to explain the condition, I am taking is a 10 volts. So here 10 volts is greater than 0 volts, means Vin is greater than V reference, means output is logic 1. So here output is logic 1. And control circuit, here whenever Vin is greater than V reference, then it will retains the present bit. So it does not change any bits. And whenever we are giving to the SAR for the first clock pulse. So we are giving first clock pulse, means the MSB bit will be set. So for the first clock pulse, MSB bit will be set. So next bits are retained as it is. Means for the first clock pulse, the SAR will be set. Basically it starts from MSB. So first MSB bit will be 1. And so let us consider these two conditions. Whenever Vin is greater than V reference and whenever Vin is less than V reference. And here for first clock pulse we are getting 1000 at the output of SAR. So whenever Vin is greater than V reference, so at the control circuit, whenever Vin is greater than V reference, it will retain the present set bit. Means it will put as is. So 1, here present set bit is 1. So it will retain as is. But whenever Vin is less than V reference, then it will reset the present bit. So here present bit is 1. So 1 is resetted. So 0. And next, when we are given to the SAR for the second clock pulse, it will go, next LSB bit will be set. So it will set 1 by 1 bit, right? So next LSB bit will be 1 and here also 1. But our output is 100, right? So 100 is corresponding voltage is 8 volts. The corresponding voltage is here 8 volts. So here 10 volts is greater than 8 volts. Means we are getting logic 0 at the output of the comparator. So we are getting 1. And here we are getting 10 volts is greater than 8 volts. Our satisfied condition is Vin is greater than V reference. So we are getting 1100. And let us discuss for these two conditions. Whenever Vin is greater than V reference and whenever Vin is less than V reference. So whenever Vin is greater than V reference, so here whenever Vin is greater than V reference, it retains the present bit. Means here present bit is 1. Means it will retain the present bit. And whenever Vin is less than V reference, it will reset the present bit. Whenever Vin is greater than V reference, it will retain the present bit. And here it will reset the present bit, right? Next, when we are giving to the SAR, it will set 1 by 1 bit. So next LSB bit will be set. So next LSB bit is 1 and next LSB bit will be sent. And 110 corresponding voltage is 12 volts, right? 110 is corresponding voltage is 12 volts. So whenever, so here 10 volts is less than 12 volts. So Vin is less than V reference, we get logic 0. So for the second clock pulse, we are getting 1100 and the output is logic 0 because Vin is less than V reference. That's why we are getting logic 0. And next, here the 12 volts. So we are getting 10 volts is less than 12 volts. Means the satisfied condition is Vin is less than V reference. So this is the satisfied condition. So for the third clock pulse, we are getting 1010. And let us consider for these two conditions. Whenever Vin is greater than V reference, whenever Vin is less than V reference. So whenever Vin is greater than V reference, here present set bit is 1. So it will retain the present bit. So 101. And here whenever Vin is less than V reference, then it will reset the present bit. And whenever we are giving to the SAR, it will set next LSB bit. So next LSB bit will be set. So the corresponding voltage of 1010 is 10 volts. So 10 volts is greater than or equals to. So greater than or equals to. Whenever Vin is greater than or equals to V reference, the comparator output is logic 1. So here we get logic 1. So the output of we get logic 1. And the satisfied condition is Vin is greater than V reference. So this is the satisfied condition 1010. Right? 1010 corresponding voltage is for the fourth clock pulse we are getting. For the fourth clock pulse we are getting 1011. So 1010 corresponding voltage is 11 volts. Means here 10 volts is less than 11 volts. Means the output of the comparator, whenever Vin is less than V reference, then logic 0. The comparator output is logic 0. So So the successive approximation register will take the nearest value which is 10 volts. So it takes the nearest one which is 10 volts. So for 4 bit it takes 4 clock cycles, right? Here we are taking 4 bits. So means it completes in 4 cycles. So 4 bit takes 4 cycles. And for n bit it takes n cycles. So whereas in counter type ADC method, so the time required, the time cycles are 2 power n minus 1, means here time period is very high. Time period is very high in counter type method. But in here it takes only n cycle, means time period is very less. So here time period is very less. Very less. And the total conversion time, the total conversion time is n into t clock. So t clock is the time period of the clock. So n into t clock, but here it takes 2 power n minus 1 into time period of clock cycles. But here n into t clock, means here time period is very less. That's why here it completes the conversion within very fastly. So the main advantages of this is it has lower conversion of time, and it has higher conversion of speed, means whenever time is very less, then the speed of operation is also very high. So higher conversion of speed. So that's why successive approximation register ADC method is widely used than counter type ADC method. And let us go for the graph. Let us take on x-axis I am taking digital output, and on y-axis I am taking analog input. Means for SAR output is 1000, and next 1100, and next 1010, 101011. So here I am taking on x-axis I am taking digital output, and means SAR output, and on y-axis I am taking analog input, which is let us consider by on x-axis 2 volts, 4, 6, 8, 10, 12, 14, and so on. So whenever the digital output is 1000, the corresponding voltage is 8 volts, right? So here the 8 volts, and next whenever we are giving 1100, 12 volts. So here we are considering 10 volts as a Vin, because Vin we are taking as a 10 volts. So Vin. So next 110 is 12 volts. So 1010 means 10 volts, and 1010 means 11 volts. So the successive approximation will take the nearest value which is 10 volts, right? Here whenever we are seeing in this case, so the digital outputs are trialed. Here we are trialing the outputs in order to balance the analog input voltage. So we are balancing the analog input voltage, and the SAR will take the 10 volts, which is nearest value. So the successive approximation register ADC method is also called as algorithm method. It is also called as algorithm method because it processes the algorithm type of applications. And so the main disadvantages of the successive approximation register method is here the blocked, so it is very complex in circuitry and the cost of production is very high. But we are used this method because of higher conversion of speed. And thank you. Any doubts? Thank you for giving this opportunity, sir.